Okay, happy Thursday evening. It's now just a little after 8 o'clock, so I will just go ahead and make a start. We already had one of these live online meetings for this week's content earlier this morning, and my plan is to keep this one tonight a little more condensed. So it's a crash course of most essential information that you might need to complete this week's material, and the little more in detail version is available from this morning's recording, and then the full version with all the finest of details is available on your Canvas course through the full lecture videos, which I have provided there. So let me just start by sharing my screen. And as we're getting ready to do that, I just want to kind of outline what I was planning to do today for this video. So I'm hoping to go through three different elements, really. I'm hoping to go through, first of all, what are the assignments for this week? So what am I looking for you to complete that counts towards your final grade? So we'll have a look of our Canvas learning module for this week. That's the very first thing. The second thing that I wanted to do today was to have a quick review of the lecture material for this chapter on fluids, electrolytes, and acid-base balance. So that's a kind of the crash course lecture version. And the final third element that I wanted to have a look tonight is all to do with our lab for this week. And this week's lab, it's going to be a little different, but it's not going to be drastically different. But there's a little bit of information, a little bit of other things that will explain why the lab is built the way it is. So that's my goal for today. And as I normally try to do, I will try to provide timestamps at the description for this video for each of those three elements, if you're only looking for one of them, so that you can just jump onto those right away. And let's share the screen. At this time, you should be seeing my screen for your course's learning modules. The section number might be different depending on which of the sections that I teach this semester you are attending, but at large, you will be seeing the same learning modules, same structure, same material there. So like I said, the first thing that I wanted to go through was to just have a quick look what it is that I'm looking for you to complete for this week's material. And if we keep going through our learning modules, we will eventually find, I believe we're now at week 11. And week 11 will cover our water, electrolyte, and pH balance. So as always, I have listed the learning outcomes. I have the lecture slides available for you as a handout version, and then I have the full lecture video. If you click on the full lecture video on the fluids, electrolytes, and pH regulation, it will guide you to a YouTube channel of mine where you will see the more nitty-gritty version of the chapter content for this week. The other thing that we'll notice is that you will only have 2 assignments for this week. So you will complete a quiz, and you're used to this quiz format from our previous chapters. So it really is not so much testing you that do you know everything, memorization, and just bang your way through it and get those points. It's much more of a learning opportunity. So as you're working through the quiz, you also have your electronic textbook available on the side. And with each question, if you get stuck on that question, you just refer to that textbook. It will actually direct you to the particular part of the textbook so you can find the answers. And this way, you're kind of reading the textbook in a guided way. And if you do that, you will get full marks for that quiz. So those are easy marks to collect. And it is a learning process. It is a learning activity to complete this quiz. Well, obviously, since we are talking about water, electrolytes, and acid-base balance in the body, these are really taking the concepts that we have seen before and looking them in a larger scale as human organism. And these are much more physiological concepts. So there is not going to be that practice anatomy activity that you're used to seeing in the homework assignment section. So no anatomy element for this week. For the lab this week, we are completing a lab that's labeled here as a critical thinking assignment. So again, I ask you to work through it. We'd work through it in a class, but if you missed that, I will set you up for success as part of this session that we have together right now. But it is an activity that corresponds to your lab. It's a dry lab, so it's really working through a question sheet that will guide you to think of the right things and consider right answers. And that way we get this critical thinking lab completed. So only 2 assignments for this week. You'll notice though that the critical thinking assignment does carry a little bit more points, so it's definitely worth completing it. And as always, I ask you to upload your answers in an electronic format on Canvas, just to keep everything more manageable. So I think that that's the first thing that I wanted to cover on tonight's session. So look at what are the assignments that I'm asking you to do. So just those 2 assignments. So I'm going to stop sharing that screen. And what I'm going to do instead is that I'm going to jump to the lecture material for this chapter and hopefully be able to share that screen with you. And it is my intention just to go through, like I said, in a very, very brief overall level, the key points of the chapter material. For a full version of the story, I refer you back to those lecture videos or alternatively to your textbook. So we're just going to use this as a quick review. I don't expect that a lot of the content that we're going to see today is ground shaking for you. I think that a lot of that you've already seen in Bio 181. We might be expanding or bringing a little bit of a different angle to that. But this is basically taking what we saw from the physiology of the urinary system and expanding it, not just considering of the urinary system, but considering the entire body. So where I wanted to start was just to highlight the concept that in a clinical setting, it is going to be important for us to be able to understand lab results. And these include, for example, labs that we can take from your blood or labs that we can take from your urine, or we could be looking, for example, on these labs, the how much water is, water content, electrolyte content, pH content, things like that. Really, the big thing there is to notice that we should have a certain numbers for these certain values. If the values are far off from where we expect to be, that can cause issues, either just slight issues or even very, very severe medical issues. Worst case scenario could lead to death. So that's why it's important that we understand the concepts of water balance, electrolytes, and acid-base balance in our body. And my Bio 181 students will recognize this picture. So I just kind of wanted to start by emphasizing how essential water is or life. So when we go to explore space, for example, you'll always hear that we're looking for evidence of water in the space. We're looking for either water that exists or water that has existed on that area. And you might ask why? Why do we really care? Well, based on our best understanding at the moment, water is a requirement for life. So rather than just searching for life, and life forms can be so numerous, so many different kinds, we're kind of simplifying our job and we're looking for evidence of water. And if we find evidence of water, we have a much greater chance then to come to the conclusion that there is life to be found. If we don't find any evidence of water, either current or past, it is highly unlikely that we will find life on those parts of the space that we're exploring. So as far as we know, most living organisms are largely made of water. There are a few exceptions there, but largely most living organisms are made of water. As far as we know, most living organisms need water to stay alive. And our understanding is that life also evolved in water. So all of those would be reasons that, again, lean us towards that let's look for evidence of water for our search of life somewhere else. And I wanted to start by kind of bringing us back to that concept that I already referred, that most of our body, most of your body volume is water. If you're a living organism. For humans, these values vary a little bit depending on the textbook that you're looking, but values somewhere within the range of 60 to 70% of your body volume being water are what I would expect to see in textbooks. So there's of course going to be a lot of individual variation depending on your body size, sex, age, activity level, where you're living, and so on and so on and so on. But at large, these are the rough percentages where we're expecting the numbers to be at. One thing that I find very interesting, though, is that the water content varies between the sexes in an adult age, and also whether you're an infant or at your older age, towards the end of your life cycle. There's also differences in water content in one's body. So let's start by looking at this sex difference first. So the sex difference that we're going to see is going to be that for males, a little bit larger percentage is going to be made of water, about 60%, whereas for the females, it's going to be around 50%. And the explanation for that is through the higher fat content in females on average, just because of the evolutionary reasons. For males, having a little bit higher skeletal muscle mass content and skeletal muscle mass then carrying the water content to the male body. In terms of the age differences that we're going to be able to see, we're going to see that infants have a little bit higher water content. This can be attributed for quite a few different things: lower body fat percentage, lower bone density, things like that. Whereas then on the older population, we're going to see that the water content is going to be less. If you're thinking of next week, and next week we will take our exam 3, there will be actually a question of ranking these adult male, adult female, infants, and individuals who are elderly in order from kind of showing that who has most water and who has least water. So we would be looking infants as the ones with the most water, then adult males, adult females, and then the elderly population. So I hope that that makes sense and is kind of a good place for us to start considering this whole concept of body fluids. Another thing that I wanted to talk about, and I'm having a little bit of trouble with my computer, so let's see if we can get it running, is that where is 60 to 7% of the fluid content that we have in the body. Where in the body is it going to be? And we'll see that majority of that, about 2/3 of the body fluid content, is going to be inside the cells. So it's going to be what we know as intracellular fluid. So just that fluid that we've seen in the cytoplasm and so on when we've discussed about the cells. The remaining third of the fluid content in the body is going to be actually located outside the cells. And this fluid that's located outside the cells, there's going to be 3 places where we find it. We find it as interstitial fluid, so the fluid in the tissues between the cells. We also find it as the plasma of the blood. There's going to be a lot of water there. And then we also find it as lymph. So 3 places where we find extracellular fluid in great quantities. And I always struggle when I'm thinking of, when we're covering these very basic concepts, am I doing a good job of explaining to you why these concepts matter? So what I'm going to share next with you is absolutely not part of the exam material. It's simply me trying to show you that this extracellular fluid actually matters. There is a direct clinical application. And we'll see this direct clinical application from an example that I picked from the work that I and the research group that I'm part of or was part of earlier, what we focused on and why the extracellular fluid was so important for our work. So I've shared with you that what I'm interested as a researcher is heart, and is the heart muscle wall of the heart, and how it behaves when there is a heart attack, referring to myocardial infarction. So when there's a lack of blood supply to that tissue. So there's basically a blockage somewhere in the coronary arteries. And what will happen as a result of that? Well, eventually that tissue will die because it's starved of oxygen, unless we do some kind of an invasive procedure to remove that blockage and bypass that blockage and re-establish blood flow to that tissue. But doing that is going to be time sensitive. So keep that on mind. And another thing that I want to share regarding to that concept is that one of the things that we see that before a cardiac muscle tissue dies, before it's dead, before it's gone, and once something has died, we cannot bring it back, we'll actually notice that there's going to be an elevation in the extracellular fluid concentration on the site that's likely to die if we do not reestablish that blood flow to that area. So we have number of hours to deal with this lack of direct blood supply to this area, and we can get an indicator of how big area is at risk based on the changes on the amount of extracellular fluid on that site that's at the risk of dying. So having said all that, let's see how it maps out in medical imaging field. Here we have an MRI image using gadolinium enhancement method of the heart. So you'll see the left ventricle nicely, thick muscular wall, and thin right ventricle muscle wall there. We're seeing the chest here, some fatty tissue on the chest as well, lungs, and liver underneath the diaphragm. So this image might seem a little weird because remember, we're looking at the heart in this particularly kind of odd angle because we're wanting to get these long axis slices against the long axis of the heart here for the ventricles. You can even see some of the papillary muscles on this image, so it's a particularly good image. But what we do with traditional MRI techniques is that we're looking for signs of the tissue necrosis on the heart muscle wall where the tissue is gone. It's dead. At the same time, I do have to put out a fact that even though there would be a little dead tissue on the cardiac muscle wall, it's not a disaster. That happens. That's something that happens. And I've seen patients even with almost up to half of the cardiac muscle wall being dead and still them being alive. Of course, there's going to be limitations what they can do, but a little bit of damage is not the end of the world. Here we see on this patient this bright spot shining up on this muscle wall of the left ventricle. And this bright spot, now in this particular imaging method, which is commonly used in MRI imaging, indicates now that this part of the tissue has died due to the myocardial infarction, due to the lack of oxygen supply, due to the lack of blood supply to this wall. So that's unfortunate. We cannot really reverse that even if we reestablish the blood flow to that side. So that brings me, of course, to think that, well, is there anything else we can do? Is this damage going to get bigger, or is this as bad as it will be? And that's really where the time sensitivity of our research group's job steps in. And it turns out that what we've been focusing on is using MRI scanners to acquire a new kind of images, not images that are these very traditional that show the dead tissue, but images that would tell us how much of the tissue is at the risk of dying. And at the risk of dying, well, we can figure that out because of what I just told you, that the extracellular fluid content changes within the tissue that's at the risk of dying. So these images are acquired with T1 and T2 method, which is a little bit different kind of a computation method, a little bit of a different image acquisition method on MRI. But one thing that you'll notice here is that there's a large bright area. Roughly at the same area where we saw the dead tissue here, we see large bright area. This is the same patient, taking images in multiple different ways. Whether it's T1 or whether it's T2, we'll see that this bright area is larger than what's already dead. This bright area tells us that this tissue is at the risk of dying. So if we are able to do some kind of an invasive procedure, reestablish the blood flow to that side, we are able to salvage all of this bright area minus what has already died. So this is really weighing those pros and cons. With every procedure that's invasive, there's risks. And now we're trying to figure out, do those risks become secondary to the benefits that we would find? And often that's the case. So all of this was possible because we saw the increase in extracellular fluid concentration at the areas that weren't yet dead, but might die if we do not react on this case. So I think that this is just an example that I tried to share to show that these numbers, these values, these concepts, even if they're basic concepts, they matter. They tell us a lot of important information. So if you didn't get anything out of that, do not worry. I would never question that in an exam, but that just shows you the idea of why we're learning these basic concepts, because they can be then applied in a clinical practice. So next thing that I wanted to talk, which is now again back to the exam material from that example that wasn't part of the exam material, I wanted to talk a little bit about, we've already established so far that water is amazing, it's important, it's useful, but consider a little bit why water is such a useful sign for us of a requirement for life. So certain characteristics of water make it so important for the forms of life that exist. So let's have a look of those just quickly together. And we're going to see that a lot of these themes I think you covered in your BIO201 classes, but we'll revisit this. So the first thing that I've listed here on my list is that water is excellent at transporting things in an organism. So this can be either through the circulatory system, where we have, for example, blood, which was largely made of water. Remember the blood plasma. And blood, of course, can transport many things such as as gases, oxygen, carbon dioxide, nutrients, waste products, hormones, and we saw even certain elements that get removed at the urinary system, so on and so on and so on. So water component of the blood is what enables the blood to carry all of these materials. But it doesn't just need to be blood. It could be just traditional mere water. The reason why plants acquire the water from the soil is not only to get the water, it's to carry the nutrients with that water from the soil to all parts, all tissues of the plant that do something, that are alive. So for example, do photosynthesis here at the top of the plant. So water is again transporting something else, in this case, nutrients with it from the soil. So we see that water is an excellent transport medium. The next two I've kind of included as a bundle. You might remember the terms cohesion and adhesion. If you remember, you're good, you're set to go. If you have forgotten that, don't worry, we're going to revisit that. So what we'll see is that cohesion referred to the concept that water molecules tend to stick to each other, tend to be attracted to form bonds. So we saw these hydrogen or these water molecule bonds when we discussed of different kinds of bonds that take place in matter. And cohesion simply, like I said, referred to the fact that water molecules were attracted to each other. So typically you end up seeing that they tend to stick nicely together. If you are curious why that happens and want to get a reminder, I will share it, but this is not something that I would expect you to be able to recite in an exam. You remember that in a single water molecule, these electrons were shared unequally between the hydrogen and oxygen, hydrogens and oxygen atom. And because of that, there was a slight charge difference at different parts of the water molecule. And these slight charge differences are now what causes the water molecules to be attracted to each other. So that was the explanation behind why cohesion happens. And you really see examples of that. For example, when you take a water glass and fill it beyond its rim, the water will form kind of this dome-like appearance on that glass. It's not going to flood over immediately because these water molecules are so closely attracted to hold together, so we can go a little bit beyond the maximum capacity of that glass. Adhesion instead referred to the fact that water molecules tend to stick to other surfaces, and especially if these other surfaces are polar. So by polar, I mean that they carry positive or negative charges. So an example of that we see if we take a drinking glass as an example again, and you kind of keep drinking from it, the water might form this kind of a reverse shape from what we saw before, where it's more attracted to the edges than to the very center part. So water is sticking to the sides of the drinking glass. And another example, that would be adhesion. Another example of adhesion is water being attracted, for example, to the spider webs. If you go out early in the morning and there's humidity in the air. So you'll see that there nicely as well. So adhesion referring to water molecules being attracted to other polar surfaces, cohesion referring to water molecules being attracted to each other. And actually, this water's cohesion is an explanation why we're going to see high surface tension of the water. So certain animals, certain bugs, for example, utilize this high surface tension of water in their mobility, moving around. So they know that this cohesion between the water molecules, or they might not know it, but they utilize this cohesion between the water molecules that they tend to stick together. They will form a tight bond that's not going to be broken if there's not too much mass put on top of it. So they're able to what we call walk on water. Another example of the high surface tension of water due to the cohesion would be if you look at people who do jumping to water as a sport or even on a holiday. If you jump to the water from high up and go belly first, you will feel that. You will feel how the surface tension of water was so hard that you might even get a little bit bruised in that impact. So that's why the people who are jumping to water from high heights, they tend to go with feet first or hands first, kind of to break that surface tension of water a little bit more before the rest of their body follows. So that's another good example of that. Water really is not soft as such. If you come from with a high enough speed, with a large enough surface area hitting the water. Another thing that we end up seeing, and this is not going to be a real estate class, but I'll use that as an example to explain this, is that water is great at storing and releasing heat. So what I've sketched here is a sketch where the red line represents temperature changes on an area, let's say somewhere like, for example, in Arizona. So during the day, temperatures might rise, it gets hot, and during the day, temperatures might drop, it gets cold. And that's just part of the daily cycle. As sun heats up, the environment temperatures go down. As sun goes down, night comes, it might get colder. And that's just the reality of the things. However, what we notice is that humans and other life forms often prefer to live close to shores, close to beaches, close to big bodies of water. May that be an ocean, sea, a large lake, or river. And why do we tend to do that? Well, there is actually an explanation behind that. Because the big masses of water over the day store some of that excess heat, so the temperatures don't rise quite as high as it would if there weren't big bodies of water around. And then during the night, they release some of that stored heat, so the temperatures don't drop down quite as much. So we get smaller fluctuation of temperatures if we are next to bodies of water. This is a good example of how water works as a great heat reservoir. We can see examples of that in the human body as well. Think of when going out to freezing temperatures, your nose, ears, fingertips, they would get frostbite. But we are able to carry some heat to those areas so that the frostbite doesn't happen quite as easily, thanks to the fact that a lot of your blood is made of water. We get that warm blood from core of our body and transport the heat with that blood to these areas as the circulatory system carries warm blood to these parts. So we're able to transport heat from one part to another with the water. I think that water radiators are a good example of this as well. So a method of transporting heat from one room to another to be able to heat up the house. So that was the fifth point that I had for characteristics of water that make it so ideal for life. The next one, I don't really know if it's going to be quite as important in terms of characteristics of water that make it so ideal for life, but just a characteristic of water. We remember that water could take different forms, different phases, vapor, liquid, and solid. So we see that with the water. And we had a great discussion in the classroom about that what happens when water solidifies, so freezes, turns into the ice. We saw that the volume of the same amount of water increases, so water expands. That could cause issues if we had, for example, gyrogenically frozen bodies, that will the water inside the cells expand so much that it damages cells. There's ways around that, and certain animals have found ways around that. So I'm just putting it out there just for the sake of completedness, that water can take different forms, different phases. What I wanted to discuss next kind of ties into the role of water as being a great transport media is that also that a lot of things can dissolve into water. So water is often referred as universal solvent. And either things dissolve completely or they don't dissolve, but they're still being able to be carried with the water. And that allows us to transport materials from one part of an organism to another part of an organism. So this is how the characteristic, these first and last characteristic kind of come together as an example of what makes water so ideal for the maintenance of the life. We are going to have some substances such as glucose, fats, urea, creatine that do not dissolve the water fully. They can be still carried with the water. So that's all good and dandy. And we're able to do this transport of these materials, for example, in the blood. So that is one option. It's probably not quite as exciting as where I'm going to go with the example of materials that completely dissolve or more significantly dissolve into water. When things dissolve into water, we will notice that they tend to have a change in the charge of these molecules or substances. So you see either positive or negative charges. And these positive or negative charges were very, very important for us when we considered that this is how we were able to establish a lot of things. For example, on a cell level, we're seeing sodium-potassium pumps, moving sodium and potassium across the cell membrane in nerve cells, neurons, establishing that negative charge about negative 70 millivolts inside the nerve cell. So that would be an example of using these charges for something, and that's how we were able to generate the action potentials, because we had that resting potential that was negative charge, and that didn't change when a nerve when a message passed through a nerve cell or a neuron. A few others that we're seeing here, we're seeing chloride in great quantities in all of the blood, plasma, and interstitial fluid. We're seeing, for example, our bicarbonate. We talked about bicarbonate as a method of transporting carbon dioxide in the blood earlier when we talked about that chapter. We can also see a few different hydrogen derivatives in the intercellular fluid and so on. But if anything you should take away from this discussion of things that dissolve to the water and form a charge, it is that water and these charged particles depend on each other. So wherever water goes, these charged particles tend to follow. Or wherever these charged particles go, water tends to follow. So water and electrolytes are connected. A term that we can use to describe is that they are interdependent. They depend on each other. And I think that that's going to be a question in your exam. So a good note to make. So we'll see examples of that in just a little bit, that how when electrolytes go somewhere, water will follow, or when water goes somewhere, electrolytes will follow. And we'll see some clinical applications of that in just a little while later on today's talk. I thought that the next thing that would be kind of a fun thing to talk about is that how much should you drink in a day? Well, it really varies greatly depending on your body size, activity levels, where you're located, many things. But the thing is that your water intake should be equal to your water loss. So as long as these two are in balance, you're not going to end up dehydrated or overly hydrated. It should be roughly the same amount of water going in as is going out. I looked at some general numbers. I think that on average, we're looking at something like 2.5 liters in a day. I think that that's just short of a gallon. I'm not very good with imperial scale, but it's a lot of water that we're supposed to consume. We're not quite, most of us, doing a great job on that. But what I thought would be fun to look at would be that how do we get water to our body? Well, drinking is going to be the most common mechanism of getting water into our body. More than half of all the water intake is dependent on that. So the sense of thirst is the driving force for getting water in. I think that this sense of thirst, often at that point, we're already a little bit dehydrated when we get thirsty. Another thing that we're going to see, about 1/3 of the water intake is dependent on the moist food products that we also consume. You might find this interesting that about 10% of all the water getting into the body was dependent on metabolic processes. So you remember earlier on, I've been writing for quite a few weeks now that formula of cellular respiration, how we take sugars and oxygen and we convert them into ATP, and as a byproduct, we're left with carbon dioxide and water molecule. Well, this water is what we're seeing now as a result of these cellular metabolic reactions. It doesn't contribute that much, only about 10% of the gain of water on average. So I guess that the next question would be that how do we then lose water? Well, we lose most of the water through urination. Again, more than half of the water loss is simply through the act of urination. Also, about 1/3 of water loss through various processes, either through skin or through lungs, breathing, either as an evaporation, sweating, or the humidity that we breathe out in just the normal breathing processes. So we see many ways of losing fluids as well there. A very, very small amount of fluids are lost as feces. So as we eliminate the non-digestible components of what we have consumed in our diet. So that is how we get water and how we lose water. And I think that the next thing that I really wanted to talk was to talk about how do we maintain the water balance in our body. And you'll see in various textbooks, depending on what textbook you look at, more complex or more simple diagrams, but there's steps, this happens, and that leads into a next thing and a next thing and the next thing. I would not encourage you to memorize these pathways. You can absolutely do it if you want, but you don't have to do it for this course. You'll notice sometimes these pathways are more of like a seesaw reactions, being overhydrated or underhydrated. You'll sometimes see them having this loop-like appearance. But at the very beginning of the course, I shared with you that as long as you learn the concept of homeostasis and this 4-step model that I introduced, you'll be good for most of the physiological processes that we see on this course. And we're going to apply this model to look at case of overhydration and underhydration in managing the water balance in the body. So you remember homeostasis was all about maintaining consistent internal environment. Your body at large wants to stay consistent. We do not want changes to happen to either direction. We want to stay where we're comfortable with. And how we were doing was that if there was a change, so that's going to be our stimulus of some kind, we're going to have sensors for it. And these sensors depended on what kind of changes we're monitoring it. But sensors simply detect it, but don't give it a meaning. The meaning to sensation is given at the level of control center. This was typically our brain, where we have some kind of a set point, the range of kind of acceptable values for this stimulus. And if we fall within this range of acceptable values, we're good. As soon as we deviate on one or another side outside these acceptable values, we probably want to act on that stimulus. And the acting happens through effectors, typically through negative feedback. So we stop that change from happening. So that's what we saw there. And I think that I was going to use this model to explain, like I said, overhydration and underhydration. We're going to start with the case where we have too much water in the body now. This is not scientific description, but we could say that the blood is too watery. And that gets detected by osmoreceptors that are located at the level of hypothalamus at the brain. So these cell bodies that regulate, that constantly scan that how much water there is in our body fluids. And we compare that against the normal at the set point at the level of the brain. And in this case, we would see that there's now too much water in the body. Well, how can we deal with the too much water in the body is through the pituitary gland producing less antidiuretic hormone. So less ADH is being produced. And you remember the role of ADH was to make us make less pee. And we saw that ADH acted on the level of nephrons, which was the structure that we had a look of last week. So now that we're making less ADH, we're now doing less stopping us from peeing. So as a result, we're actually producing a great amount of urine, and we try to urinate out some of that excess water, and in this way stop this too much water in the body from being the case. So you'll see how we were able to simplify a previous diagram that was much more complex by having just these 4 different steps. And you won't be surprised that we'll see if we look at a reverse of what could happen. In this case, we have too little water in the body, following very similar pathway. The osmoreceptors at the level of hypothalamus sense that. We compare it to the normal at the level of the brain, and the act that we're going to do, the effector is going to be now pituitary gland releasing more ADH, antidiuretic hormone. And you remember that antidiuretic hormone turned the distal convoluted tubal walls of the nephron porous. So now we're recovering a lot of the fluid from the nephron back to the circulation before it becomes urine. So we're kind of saving the little water that we need. So you will end up as a result producing less urine. And in this way, we're kind of trying to stop this little water situation from getting worse, or hopefully even improve it. So I hope that that makes sense as an explanation of how to simplify some of these diagrams that you see on your textbook. And next thing that we had a look of in the class was the concept of tonicity. And you might remember the tonicity from your 181 or 156 classes. So what we're seeing here is based on very simple basic concepts. So you remember that materials move from areas of high concentration to areas of low concentration passively through the process of diffusion. So we don't need to invest even any energy onto that. That just happens. And this is what we're going to see now when we look at the movement of water as a result of where the electrolytes are located. So where these charged particles are located. So we're going to see good examples of that in 3 different cases. So let's start with hypotonic conditions. In hypotonic conditions, the inside of the cell contains now more electrolytes than what there are electrolytes outside of the cell. So your body will automatically try to neutralize this difference, make it even on both sides. And the simplest way is by letting more water enter into the cell. So the cell is gaining more water, and it grows in size, it swells, and it might potentially even end up bursting. That would be sad, that would not be good outcome. So one of the things that we discussed in the class was that always make a mnemonic. Whatever helps you to remember the concept, do that. So in case of the hypotonic cells, I have chosen that for me it works to think of hypotonic cells, that okay, let's think of a word that sounds very similar, an animal. I think of hippos. Hippos in my mind are these big animals that look a little bit like swollen cells. So my hypotonic conditions told me about hippo cells, big swollen cells. Whatever works for you to remember it, that's what I ended up picking. The next condition that we're going to see is the case where we're talking about isotonic conditions. Now, in isotonic conditions, there's just the same amount of electrolytes outside the cell as there will be inside the cell. Since this amount is the same, there's really no net gain or net loss of the water to the cell. Some water will always get in, some water will always get out, but the cell remains the same size. So there's no change in the overall cell volume. So how do I remember this? I think of the word isotonic, and I think of the cell telling me, saying that I so perfect. So isotonic cells are perfect cells. They don't need to change into anything. They're excellent as they are. They remain the same size. And the final condition that we could see was a condition where we have hypertonic cells. In hypertonic condition, the outside of the cells has more electrolytes than the inside of the cells. So now we're again trying to balance this difference outside and inside. And the easiest way we can try to balance that is by diluting the outside of the cell, by pumping water or letting water leave from the cell to the outside the cell. So water is now flowing out of the cell. Cell will shrink in this process, and it might potentially even end up drying up. That would be kind of not a great outcome. So how do I remember hypertonic cells? Well, I think of what kind of people are people who are hyper. People who are very hyper, they have a lot of energy. What do people who have a lot of energy do? They run around a lot. And what happens if you run around a lot? Well, you become very skinny. So hypertonic cells, in my mind, are these skinny cells, cells that shrink. So whatever helps you to remember these, please come up with your own mnemonics, but those are some examples that I wanted to share with you in case you find it useful. It's up to you. I would never expect you to use the same mnemonics as I use, but I want to throw some ideas out. And this tonicity concept, we can actually see it in real life when we have a situation where someone, let's say, for example, is either exercising or working outdoors on a hot Arizona day. Well, in this process, you will end up sweating a lot. So you're losing fluids. And with the fluids, you're also losing electrolytes. So most natural response to that would be to drink more water to replace that lost fluid. What happens actually if you just drink a regular water and you've been sweating a lot is that, yes, you get the fluids up, but the body fluids become now too dilute. There's not enough electrolytes there. So your brain, the osmoreceptors at the hypothalamus will now be like, oh, our body fluids are too dilute. We need to neutralize that. So let's get rid of some of the water by making you urinate. And again, you went from the stage of being dehydrated and trying to fix it with drinking just regular water to making the dehydration even worse, even though you were trying to fix it. So how we get around this is that we don't drink just plain old water if we're losing great quantities of fluids and electrolytes with those fluids. We must drink drinks that contain electrolytes. So this is where athletes who push their body to the maximum might turn onto the recovery drinks or electrolyte drinks. And these contain these electrolytes that we lost with the sweat in great quantities to kind of bring us back where we should be. So by drinking, not becoming more dehydrated. And I did have a look of 2 different kinds of electrolyte drinks. Big take-home message rather than promoting one brand over another is that notice how little electrolytes we end up finding in juices and soft drinks. It's really using these drinks that are designed for this replenishing, replacing lost electrolytes, which is the best solution there. So you shouldn't have to rely on electrolyte drinks in your day-to-day life, but if you are losing a lot of fluids and losing a lot of electrolytes, then that might be a useful option to explore. So here we see especially the sodium and chloride and so on as examples. So the last concept or last theme that I think that we discussed in the class was to do with the acid-base balance in the body. So we started by just reminding ourselves about the pH scale from 0 to 14. Around 7 is the neutral. You can have acidic concentration or basic concentration in the substance. One good way of thinking of the pH scale is remembering that H stood for hydrogen ions. So we're looking at the amount of hydrogen in that substance. And the pH scale is not actually a linear scale. It's kind of more of an exponential scale. So you cannot say that pH 4 means that there would be twice as many or there would be a twofold difference when compared to the pH 2 in the quantity of hydrogen ions. That's not really what's happening here. It's more of an exponential scale. But what we end up seeing, what's quite remarkable, is that your body is able to maintain its internal environment within a very, very narrow range of pH. So somewhere around 7.35 to 7.45, so 0.1 unit of a variation. So that's a very, very small variation. If you've ever tried to mix substances in a chemistry lab and get the pH within this narrow range, you know that that's a hard task. So somehow our body is able to do this amazing accomplishment. And we need to think of how does it do that. You'll also notice that the survival range, if you go anywhere below 6.8 pH or you go above 8 of a pH, you will end up at these points being sick and potentially even dying. So there is some amazing mechanism how our body is able to maintain this pH balance in the body. And we're going to have a look of that. Before we have a look of that, I just want to show you that these are clinical conditions. If your pH values are too high or too low, alkalosis or acidosis, and we'll see some of the signs and symptoms of those in a second. But this is the way. There's actually 3 different mechanisms that play a role in maintaining your body pH within this very, very narrow range that we saw. And let's have a look of those. So the first mechanism that we're going to have a look of is through buffers. So buffers are just chemicals that bind with acidic or basic substances, bringing their pH close to 7, so that neutral value. These act very fast and are very quick response to pH changes, so we consider them often as our first line of defense against the pH changes. Respiration is another way to make changes. It's a little slower. We're talking of minutes before we're able to adjust the amount of hydrogen ions. But again, the center at the brainstem for the breathing regulation would now detect the excess or the lack of hydrogen ions and then adjust the rate and depth of breathing to deal with that, to get rid of some or maintain some. So respiration is kind of a slower mechanism, if we wish to describe it in that way, for dealing with maintaining the pH within a desired range. The third mechanism, the renal mechanism, you'll be familiar with that from our last week's chapter where we looked at the kidneys and urinary system and how kidneys were able to remove excess hydrogen ions from the blood through their function and through their work. Of course, the trouble is going to be, even though we can pee out excess hydrogens, This is a slow mechanism. This takes from hours, even to days to work. However, this is the most powerful, most potent mechanism for maintaining the body pH. So by this interaction of 3 different mechanisms, we're able to keep the body pH within this very, very narrow range that we're seeing here. And that brings me to just show some clinical signs and symptoms of acidosis and alkalosis. They start with very not so dramatic initial changes, just feeling a slight headache, confusion, lightheadedness, a little drowsy, but can get very severe loss of consciousness, muscle twitches, loss of sensation, vomiting, nausea, arrhythmias, seizures, or in the worst case, even coma. So really, there is a reason why we don't let this happen. This could be lethal. So that's where those 3 amazing mechanisms that we saw that we had for maintaining the body pH within a narrow range becomes so important. And I wanted to wrap up this kind of a review of the lecture material by showing this slide that, of course, one of the first things that you get done to you if you go to a medical professional and you're feeling sick, you're feeling unwell, we often put you on a drip. And this drip is not going to contain just any old water. It's actually contents that are perfectly balanced with the electrolyte needs or contents of the ions in your cells. So we're not ending up with this tonicity change. It's perfectly balanced, sterile fluid. So we're able to add fluid to your system, bring up your blood volume. If you are dehydrated, very, very fast with this IV fluids that we're putting to your body. The other thing to notice there is that we do that also because now we have a direct route to bring medication to your bloodstream rather than giving you a pill and having to wait even up to hours for it to have an effect. So that's another reason why we end up using the fluid therapy so much in clinical practice. And that really summarizes the lecture content that we covered in a class. I know that we typically use these review sheets. I'm not going to load these online for copyright reasons. I had some bad experiences of them starting to be spread around internet. But if you did miss a review sheet, you can definitely get that next time that we meet as a class in a classroom setting. So that's going to be made available for you. And that concludes everything that I had in terms of the review of the chapter material. As always, I saw that we had someone joining us, so I appreciate that. As always, I welcome questions. Just to give you an idea what was the structure of today, I was going to next talk about a third topic for this session. And the third topic was to have a bit of a look of our lab for this week. And I'm just going to share the view of the learning module for this week. And just as a reminder, I know I mentioned this at the beginning of the recording, I'm only asking you to do 2 assignments this week. The first one is the quiz. You've done quizzes before. That's a learning activity, not just like testing that you should know all of the answers, but as you're completing the quiz, you're actually working through the chapter material in an electronic textbook. So it's worth doing that. And the second is a critical thinking assignment. That was our lab this week in a classroom. So if you didn't get a chance to join us for that, you can actually still complete it yourself. You'll find that there is a worksheet that you will work through. And I've also provided kind of a nice breakthrough of the points that are available for you. So there's going to be 4 different sections. And for each of these sections, I'm looking for you to provide certain answers. You'll notice that there's always an odd, weird row of points after a set of points. Do not worry about those. I will explain why they are there in just a moment's time. But for now, you can just simply ignore those. You will simply download the worksheet from here by clicking to this critical thinking. If you have any questions, feel free to just shout out, unmute yourself, or write them to the chat. Otherwise, what I'm gonna do is that I'm actually gonna work through the lab with you so you have a chance to look at those if that helps you. So I'm gonna stop sharing this screen and just to share a PowerPoint that I prepared regarding this lab. And I'm just going to explain a little bit about why this lab might look a little weird just quickly. Remember that this session will be recorded, so you'll be able to go back if you missed anything, so do not feel intimidated in that sense. I'll be uploading the recording as soon as we're finished and it uploads to the YouTube. But let's have a look of the lab. And some students sometimes are like, oh, this is, of course, I appreciate you. This lab seems weird, students sometimes say. And it is true. This lab is a little different because of the purpose why we do it. So other than just serving as an activity that you do that carries points towards your final grade, there is a secondary purpose for this activity. So all community colleges in Arizona and in several other states are accredited by an organization. And one of the most common organizations for us is Higher Learning Commission. What Higher Learning Commission does, they come every now and then to the institution and they look at what are our learning outcomes for a course? How do we teach it for you? What textbooks, what materials do we use to do that? How do we assess what you're learning? And kind of really just look at that we're doing our job correctly. So it's a great thing to know that your institution is accredited. But for them to be able to do that, they ask us to provide data for them and check on things every now and then. And every single class in this college has one critical thinking assignment as part of the course. And every section of BIO202 does this same critical thinking assignment. So we will never share your grades for this particular assignment with anyone else. We will simply collect the grades from all of the classes, all of the sections, and put them together over multiple years, and then send that data or analyze that data. And what we're wanting to see with that data is that students are successful in their critical thinking skills. So that students are able to be given data and they can draw conclusions out of it. Or they are able to be given a case scenario and then they can draw conclusions out of that based on what they have learned before. So it's rather than us testing that did your memorization work, we're testing that are you able to create new information based on everything that you've learned. So that's the point behind the critical thinking assignment. It has no effect to you. You will just do the assignment as you would always do a lab and you'll be totally fine. I'll have to do a little bit of behind the scenes work to collect that data and send that data onwards, but it's going to be completely anonymous and it's going to be aggregated data. It's nothing of yours will be shared so that you can be identified as yours. So I already mentioned about the grading matrix. You'll be just focusing on these traditional numbers that we've seen before. Never mind about the second row after everyone. But I do think using those grading matrices is sometimes very useful because then you know exactly what the person grading your assignment is looking for you to do. So this critical thinking assignment is really a case study. And in this case study, we're going to be looking at fictitious story of two ladies, Carla and Maria, who went for a hike from one rim of the Grand Canyon to another rim of the Grand Canyon. This was about 24 miles long hike. And for our purposes, we can assume that Carla and Maria are perfectly similar in so many important characteristics. Their same age, their fitness level is the same, they train similarly, they are just similar. The only difference that we're gonna see with Carla and Maria is that one of them is gonna be drinking way too much water during this hike, so they're gonna become overhydrated. And one of them is not drinking enough water, so they're gonna become dehydrated. And what we're trying to do and encourage you to do is to see what kind of effects overhydration or underhydration would have on these individuals and on their well-being and on various factors that we can monitor out of them. So, like I said, there's going to be 4 parts to this case study, and we'll go through each of these one by one. I will put this out at this point. I am not expecting you to be as wordy and as detailed as I have been when I've provided some sample answers to you. Instead, what I'm expecting you to do is just to pick out the key point from those answers so that you know whether there were changes that were something increasing or decreasing, or did it stay stable. And then you can just, even by using abbreviations or bullet points, give me 2 reasons why you came up with that conclusion. And critical thinking assignments are kind of fun in a sense that you don't even need to get a correct answer, as long as you can justify how you ended up with the answer that you're giving to me. So just pick what you think will happen and give me some reason for it. You don't need to go into great amount of detail. All I need to do is to see that you feel that there's some logic behind your thinking process, and you'll get full marks. You know how I grade. I'm gonna be generous and helpful on that sense. So the first part of the assignment provides you a list of pre and post hike information. So various different measurements that we've taken. From the pre-hike data, you can see that Carla and Maria are very, very similar. Their weight is the same, their height is the same, their sweating rate is the same, their pace of hiking is the same, their blood calcium amount is the same. So they're just a complete match. So we're comparing apples to apples. We're comparing something that's similar with another similar thing. What I'm asking you to do in part 1 is to identify if there's any values that appear abnormal. Well, there's not going to be abnormal pre-values, but there's going to be some abnormal post-values. And how you identify them and how you answer to me in the lab report, you can simply circle or you can simply highlight whatever you think is an abnormal value. If you want to tell me that it was a high value, or if you want to tell me that it was a low value, you can simply draw an arrow that points up or down. You can use circling of the answers, you can use underlining of the answers, however you wish to do it. Just mark it somehow on that table and I'll be able to give you your points. That's all I'm asking. So you can indicate to me as well, other than just it being abnormal, why was it abnormal? Was it too high? Was it too low? Many students prefer using arrows to just point that out, but you can use also abbreviations, writing high, low next to it if you prefer. And that's the first part of this part 1 activity that we'll do. C is a second part of part 1 activity where I'm actually asking you to also pick some important values that would give you indication of water balance in an individual. And again, you can simply just highlight those or circle those. And we'll go through both of these. So let's have a look at some of the tables. These tables are just directly from your lab assignment, and you'll see that we are providing you normal values against which you can compare these post-hike values. And again, remember, you do not need to get every single detail. All you need to get is some of those and show me that you are doing critical thinking. And as long as you do that, you'll get full marks. So let's have a look of a little bit of together which of these post-hike values would seem abnormal and why. So for Carla, we're seeing that Carla's heart rate is quite elevated at 200 beats per minute, when the normal heart rate should be around 60 to 80 at rest and less than 195 at the maximum exercise. So Carla's heart rate is definitely high. That's elevated. So if you want, you can just mark it like that. Another thing that we see is that Carla's blood pressure is on the lower side. You remember normal blood pressure is 120/80. For Carla, it is 100/65. So that's definitely on a low side at the end of the hike. So that would be abnormal. So in this case, we're marking that it's a low value. If we're looking at Carla's plasma, and sodium concentration there, we're noticing that the value that we're getting there is 147, whereas the normal range would be between 135 and 145. So it's a little bit on a high side. So it's slightly elevated for Carla, the plasma values. If we look at the urine osmolarity, we're noticing that a normal urine osmolarity would be somewhere between 280 and 295. In case of Carla, that's actually 1400. So that's definitely an elevated value. So again, you would just mark those, and that would serve you as having spotted some abnormal values for Carla. I think that there's some other ones that students found for me. I just didn't pay attention to those, but you could see other things. You shouldn't be dizzy, nauseated, extremely weak, or lethargic. That would be weird. Something's not right if someone has those symptoms. So those all would be things that we want to highlight for Carla. Let's have a look what we can see for Maria. What's interesting with the Maria is that it seems, if we look at her weight, it seems almost like Maria gained extra weight during a day-long hike, 8-hour-long hike. That doesn't make sense. You're not going to build that much muscle in 8 hours. So what we're seeing actually is that Maria drank so much water that her body is now heavier because there's so much water inside there. So her weight went up by 1.5 kilos. So there's something weird in there. So we can highlight the weight, that's elevated. Something is happening. That shouldn't normally happen like that. We also see from Maria's blood pressure, which is 140/90, that's elevated. That's higher than what it normally should be. So that's a high value. If we look at Maria's plasma concentration, that's 125, whereas it should be between 135 and 145. So that's definitely decreased plasma concentration that Maria has. So on the lower side. If we look at the urine osmolarity of Maria's, that's also decreased at 100, whereas it should be somewhere between 280 to 295. So this is definitely a low urine osmolarity that we see with Maria. And again, we're seeing things such as symptoms, headache, vomiting, lethargy, confusion. These are not what we're supposed to see. Something's wrong with Maria. So it is as simple as that. That's what I'm looking for evidence of your critical thinking for the first 2 parts of the part 1 questions. And I'll come back to this in just a second. But for identifying abnormal post values and indicating whether those values are higher or lower than normal. So you've already knocked out A and B out of the park if you completed that with me as we were through it. If you have questions at any part, just feel free to unmute yourself and shout out to me, and I will definitely try to help. I'm not trying to ignore you. I try to be also mindful of your time and not to go and dwell on things. And so let me know if I'm going too long or too slow or whatever. The second part of the part one question was for us, and I'm going to go back there, to indicate which of the values are relevant to the water balance. And again, you can simply highlight these on your answer sheet. So let's have a look of these together. Some of the indicators of one's water balance in the body would be their sweating rate. So whether they're sweating a lot or whether they're sweating abnormally little, that would tell us what's happening with the fluids in their body. Your heart rate will give us also information about one's fluid balance, because you remember, if you are very dehydrated, you will have very little blood in your vasculature system. So your heart rate has to compensate with that. Or if you are overly hydrated, you now have almost too much blood in your cardiovascular system. So your heart rate needs to compensate for that. Same goes for the blood pressure. So again, we see that tells us what's happening with hydration level of someone, if there's too much or too little water. The plasma values, again, you can get too diluted or you can get too concentrated, depending on how much water you have in the body. Same goes for osmolarity. Blood volume goes with what we discussed with the heart rate and blood pressure earlier on. And of course, the total body water content would be also a good indicator of one's water balance. One thing that I didn't have on these tables that I thought would be appropriate as well would be looking at urine concentration. So that would be another thing that we can consider. But like I said, you don't need to get every answer. You just need to get some of those and show me that you're doing that critical thinking. So this table or these highlights combined with the previous highlights would be a perfect answer for the part one of this worksheet for this critical thinking assignment. I hope that that makes sense. And like I said, at any time, feel free to shout out if you have questions. Otherwise, I'll just keep going on. And like I said, you will always be able to access these also as recordings afterward. So let's have a look of the part two of this activity. And this part two looks at both Carla and Maria, who faced different kinds of challenges, although they were similar in all important starting characteristics in early part of their hike. So now they've hiked only about 6 miles or so. And what we're going to be doing, we're going to be looking at what happens to these various values in their body. And these values have been listed in your handout as A, B, C, D, and E. So we're looking at the heart rate, blood pressure, ADH, hormone concentration, angiotensin 2, and aldosterone. You'll notice that angiotensin 2 and aldosterone go kind of hand in hand a lot of the time. So again, just to reinforce, I'm simply asking you to tell, are these elevated or decreased? So that's all I'm asking. And then I'm asking you to give me a couple of examples or reasoning, a few points of reasoning, why something would be elevated or why something would be decreased. You do not need to go in as much detail as I'm going in these sample answers. So keep it simple and you'll be good. So we're going to start by looking at Carla at the early part of her hike. What we'll notice with the Carla in this scenario is that Carla actually had a leak on her water container. So she has lost water throughout her hike, this early part of the hike. She's been kind of worried about the fact that she doesn't have enough water with her. So she's decided that she's going to drink only very, very small amount of water. So her total water intake during the first 6 miles is 250 milliliters. That's about a small drinking glass. So if you are exercising a lot, hiking a lot, and you're not drinking enough, what would be the immediate changes, immediate symptoms that we're seeing? That's what I'm asking there. So let's go through the answers for the Carla, part 2, section A. So her heart rate would probably be increased. And her heart rate would be increased simply because of the fact that she's exercising. So she's being very active, so her heart will work a little faster. So the heart rate is increased. We're not seeing big effects due to dehydration at this early part of the hike. They will come a little later. And we'll also notice that Carla's blood pressure is going to be increased. Again, because she is exercising, so her heart needs to beat a little bit faster, her blood pressure needs to be a little bit higher so that we're able to carry oxygen, nutrients, all these things to those active tissues at the rate that meets the need of those tissues. So for example, her muscles are now working hard, so we're carrying a lot of blood there, also at the higher rate. So both increased because she's exercising. That's the amount of detail that I'm looking. I just provide a lot of detail on these explanations because I was a little extra when I was writing those. Let's have a look at what's happening to Carla's antidiuretic hormone amounts. The amount of antidiuretic hormone is probably going to be increased. And this is increased because she's not getting enough water. She's sweating more than she is getting new water in. So to deal with this kind of water loss that she's dealing with, your body is now producing more ADH, antidiuretic hormone. So we're trying to maintain the little fluid that's there by making sure that she doesn't pee as much. So that's why the ADH hormone amount is increased, because she is losing more water than she's taking water in. What we're going to see with angiotensin 2 and aldosterone 2 is that both of these are likely to be elevated. That's because now she's exercising, and that decreases the blood flow, and that decreases the glomerular filtration rate, and reduced glomerular filtration rate then will have an effect combined with the vasoconstriction that it will stimulate release of hormone known as renin and increased release of angiotensin 2. We're seeing this kind of coupled with aldosterone because angiotensin 2 is elevated, and that stimulates the release of aldosterone from the adrenal gland. So what should you answer for the D and E? You should answer for both, that they are likely to be elevated. And this is because of now this exercising and how these hormones are kind of a pathway where one affects another. So if you are providing me an answer that resembles that, that's enough of a detail. You don't need to be this precise as I went here. Like I said, I was a little overly excited of this assignment. So I hope that these help for tackling the part 2, section A, where we're looking at Carla's situation. And what I was going to do next is that I was going to move on to look at Maria for the part 2. And again, if I'm going too fast, I'm happy to slow down. Just let me know. Like I said, I will also provide a recording afterwards. So let's have a look at what's happening with Maria at this early part of the hike. The situation is a little different with Maria. Maria has been actually drinking a lot. And her total intake of the water is about 1 liter per hour. So she's consuming more water than she loses. And because she's consuming more water than she's losing, she's now, body is starting to want to get rid of that excess water, and she's starting to feel a need to have a pee, to urinate. So let's have a look of what would happen to these various values if you are drinking more than you're losing, but the situation is not really bad yet. This is the early situation. Well, your heart rate is going to be increased again, and the heart rate is not really because of the water consumption. It's just increased because our Maria is now exercising. So she's working hard. Her heart is responding to that physical exercise by increasing the heart rate. She is also seeing this increase in blood pressure for the very same reason. She is exercising, and in response to the exercising, her blood pressure is going up, so that we're able to provide enough perfusion to the tissues such as muscles that she's using as she's exercising. So there is going to be increase on both heart rate and blood pressure. Well, we're now going to see what's happening with the ADH, antidiuretic hormone values. Those are probably going to be remaining the same as they were before embarking on this hike. And this is because she's probably ingesting close to the same amount of water that she has lost. She might be ingesting a little bit more, but it's not that much more that our body would be worried about that. It's just like, okay, you're getting some water, but it's kind of a little time that you've been getting a lot of water, so we're not worried of that yet. We're just going to keep the antidiuretic hormone levels the same. So this is because, like I said, the difference between what she's taking in and what she's losing with the water is not drastically different. So they're both those values that we're worried and we try to control with ADH, they're still within the normal range. So there's no need to do any changes to the ADH hormone amounts. Everything's normal at this point. When it comes to the angiotensin 2 and aldosterone 2, both of those are likely to be elevated. And I think we're seeing the same answer that we saw in case of Carla for angiotensin 2 and aldosterone. So again, she is exercising. So in response to that, the angiotensin 2 goes up. And in response to angiotensin 2 going up, the aldosterone is going to go up as well. So Maria is exercising, and this will mean that there's going to be less blood flow to the kidneys. So the kidneys glomerular filtration rate is going to be decreased as well. And because the glomerular filtration rate was decreased, there's some vasoconstriction as well that will cause renin to be released and also angiotensin 2 to be released. And if angiotensin 2 is being released, so those values are elevated, that will then stimulate the release of aldosterone from the adrenal gland as well. So again, for the D and E, all you have to do is tell me that both of those are going to be elevated because she's exercising. And because she's exercising, our kidneys are not as active. That's it. I went crazy with my explanation because, I don't know, I was optimistic about life and I had a lot to say at that point. But this is the level of detail that I'm looking for the part 2. So that concludes our part 1 and part 2 of this activity. And if it's okay, I would like to move on to the part 3. But as always, if I go too fast, if I'm not clear, feel free to stop me. Remember, I'm not looking for perfection. I'm just looking for you to make some sort of a decision and then back it up with something. It can literally be abbreviations. That's your justification for your conclusion. You don't need to write full sentences or anything like that. So let's have a look of the part 3. Part 3 is looking at Carla and Maria now late into the hike. So they have hiked almost all of the hike. They're about 20 miles completed out of the 24 miles, I think that the total length was. So we're going to look at these same values: heart rate, blood pressure, ADH levels, angiotensin 2 levels, and aldosterone 2 levels for both of them. But remember that they had a different problem. One was getting dehydrated, one was getting overhydrated. So we're going to see some interesting changes now that this dehydration and overhydration has been going on for quite a while, several hours. We're talking of 6 to 8 hours that they've been in this condition, and they've been really working hard during this time. So let's see what happens. And the story or the clinical scenario, the case study that we're being told tells us that at this late part of the hike, Carla is now starting to feel thirsty. because she's losing that water from her water tank. And even though she was able to fill it, the water tank at halfway point of the hike, she is still worried of not having enough water with her. So she's only very, very occasionally sipping some of the water from that tank. And she's also occasionally sipping a sports drink, which is going to be high in electrolytes, like we saw in the lecture portion of this chapter. She's occasionally sipping that, but she's not getting enough water. She has taken in about 1 liter of water and sports drinks. So the volume of the fluid that she's taken in is about 1 liter. So that's not a lot for an 8-hour hike. I think that she would have sweated at the rate of, it tells you on the assignment, at the rate of 250 mils per hour. So she has been sweating a lot more than she has been drinking. Another thing that we're going to see is that Carla has also urinated. She urinated at the beginning of the hike, about half a liter, and then she urinated at the end, towards the end of the hike, another 250 mils. Now, when she urinated towards the end of the hike, her urine was very dark yellow. So that's already telling us that she is dehydrated. So she has lost way more fluids than she's taken fluids in. And we're going to start seeing that there's significant changes in all of these: heart rate, blood pressure, ADH, angiotensin II, and aldosterone levels. Let's have a look at those. And again, remember, you don't need to go into as much detail as I've gone here. So we're going to see that for Carla at the late part of the hike, when she's getting dehydrated. What's going on? Well, her heart rate is going to be increased. First of all, it's increased because she's still exercising. But another reason why her heart rate is going to be increased is because she is losing blood plasma. So she's not getting enough fluids. So she's now starting to get dehydrated. Because her sweat loss is greater than her fluid intake, she is now having less volume of blood in her cardiovascular system. So in response to that, as the stroke volume decreases, also the cardiac output will decrease. This will then cause heart rate to go up, so that we are still getting enough blood to all parts, even though there's not enough blood to go around to all parts of the cardiovascular system. Well, we simply try to pump that blood now faster because we're short of blood, because she is so dehydrated. So heart rate is up. Heart is working really hard for 2 reasons. Carla is exercising and she's dehydrated. So we try to compensate for the lost fluid, lost volume of blood, by pumping that blood faster around the body. So that's the first thing that we see. Second thing that we're going to see is that her blood pressure, it's either going to be normal or it's going to be slightly decreased. And let's have a look at why that would happen. Why would Carla at the late hike have low blood pressure, or a normal-ish blood pressure? Well, this is all dependent on whether the heart rate is enough to compensate for the loss of the fluids. If there's too much fluids lost, well, then Carla will have an issue that her blood pressure might be slightly dropping. But the drop is not drastic. But we're seeing kind of a normal-ish blood pressure or slightly decreased blood pressure because she has lost so much of fluids. Her blood volume is lesser, and it's just depending on whether we're seeing a big change in blood pressure, that how drastic that loss is and how much your heart is able to compensate for that loss through increased heart rate. So that kind of depends. What are we going to see with ADH hormone amounts? Well, the amounts of ADH hormone in case of Carla are going to be through the roof now, because she is very dehydrated. So there's going to be a lot of antidiuretic hormone. Because she has lost so much fluids and she hasn't been able to replace those lost fluids, now we have very little plasma volume. So in response to that, your body tries to kind of retain that last of the fluids. And how we retain the last of the fluids is that we produce anti-diuretic hormone with the goal of stopping her from urinating. So let's save all of that fluid that she so desperately needs. In terms of the angiotensin II and aldosterone, both are going to be increased, and for the very same reason, because there's less blood volume, there's less blood pressure. This will then increase renin secretion and angiotensin II production, and increased angiotensin will cause aldosterone release to also go up. Again, don't worry about getting all the nitty-gritty detail. For your answer, I'm looking that you are able to tell that both angiotensin II and aldosterone are going to be elevated. And this is because she is so dehydrated. And this dehydration is now affecting her blood volume and blood pressure, which both have dropped. So to deal with that, we're getting now angiotensin and aldosterone levels going up higher and higher. I hope that that makes sense. Again, I will provide this as a recording as well, but keep it simple. Just tell me whether something went up or whether it went down and why. And it doesn't even need to be full sentences, just kind of a rough idea what led you to give that answer. Let's have a look what's happening with the other girl, Maria girl, at the late hike. So about 20 miles in. What we're seeing with the Maria is that Maria was very proactive. She read that dehydration before her hike. That dehydration is one of the big concerns when hiking for long periods of time. So she set on this hike with a mission that I'm going to drink a lot of water. She had a goal of drinking 1 liter of water every hour, which is a lot of water. And she hasn't been able to do quite that, but she has been drinking a lot. She has drank in total about 6 liters of water in this short day hike. When she reaches this 20-mile point, now she has consumed so much water, so much more than what she has lost, that we're starting to see some signs and symptoms of water poisoning. She is developing a headache. She's feeling a little bit nauseous. She's not hiking quite as fast as she was hiking before, but she's still maintaining some of that speed. Her sweating rate is about the same, or probably she's sweating a little bit more than she was before. She has urinated twice. 1/2 liter on each case. That's a lot of urine. And her urine was light in color. So we can tell that she was very well hydrated. Your urine, if it's very, very light in color, that tells us that you've got a lot of water going around there. So now let's see if she has been taking this excess water for quite a while now, and we've done that for quite a bit. What's happening with these 5 different measures? And again, remember, I simply want you to tell whether something went up, down, or remained the same, and why. And the why can be very, very short explanation. Let's have a look what's going on. Maria's heart rate has likely decreased. Even though she's exercising, which should be bringing up the heart rate, she has now taken in so much fluid, so much more than what she's losing, that her total blood volume is up. Her heart rate might be still up, but it's not up a lot. So it has gotten down. It has gotten down from what it was before. So really, to summarize the answer, heart rate has dropped, and it has dropped even though she's exercising. She has now so much more extra fluid going around in her body that her total blood volume is up. And for that reason, her heart now beats at the lesser rate. to kind of compensate that excess fluid. We're going to see that her blood pressure has increased because we have now way too much fluids in the body. That way too much fluids in the body is also going to be seen in the blood volume. And because the blood volume is so high, now the blood pressure is going up. We need to pack all that blood within the same amount of vasculature. So it's going to be packed in a greater amount in a same amount of space, so the pressure is gonna be up. It's gonna be elevated, increased. What's happening to ADH hormone amounts? The amount of ADH hormone has decreased. This is because she has taken so much water that her plasma is very diluted. The plasma volume is up. These both inhibit ADH secretion. So if you have dilute plasma and your plasma volume is up, your ADH secretion will go down. So that's the explanation for that. Let's have a look at the angiotensin II and aldosterone. Both have decreased because the renal perfusion is increased, parareceptor input is decreased. These both lead into lower renin release and lower angiotensin II production. We're also seeing that because angiotensin II production is down, aldosterone production is going to be down. So both angiotensin II and aldosterone are going to be decreased because we now have so much excess water in Maria's body. I hope that that makes sense. Like I said, you don't need to go into great detail. You just need to have the big picture of the story. So that completes our part 3. And let's have a look at the part 4. And part 4 is really a simple part, what we're going to do. So what we're going to do at the part 4 is that we're going to look at what's happening. I shouldn't have had that slide there. Let me just fix it. So we don't need this slide. We have now completed the hike. And we're wanting to see 2 things. Why one of the hikers lost so much weight and why one of the hikers gained so much weight in this short period of time of 8 hours. 8 hours is not enough for you to lose adipose tissue, so to become skinny. So it's gonna be all about water. If you lose weight, you have now become dehydrated. And this is actually what we see when someone goes on a diet. The first week, the weight drop is fast because you're just losing the water from your body. The other hiker is going to be actually gaining weight. And again, in 8 hours, you're not going to build big muscles. What we're seeing is that she's gaining weight because she has so much water inside her compared to what it was before. So those are things that we're going to look, and we're going to look for signs and symptoms that explain why this happened. So let's have a look at the story a little bit, what's happening in this storyline that we've been looking at the end of the hike. Both Carla and Maria end up stumbling into a ranger, and this ranger is like, oh, these girls are not doing well. Let's call 911. Well, medical professionals will come and they will take vitals from both Carla and Maria, and they will also do some other important lab measurements. And all of these measurements are shown as these post-hike data on your handout, the first page. So all of that information is given there. They also will determine that Carla is going to be most comfortable if she's laying down, whereas Maria is going to be more comfortable if she's sitting up. So all of these things are clues that make us think of something. And let's have a look at what it makes us think. Well, in case of Carla, what we're going to see is that Carla has lost more fluids and she has been taking fluids in. So she has been getting dehydrated throughout this entire hike. That's why, because she has gotten so dehydrated that she has lost a lot of fluid that you should naturally have in your body, she actually will have a lower weight at the end of the hike than she had before. This is not because she became fit. This is simply because she is so dehydrated. So that's the answer to question 2. Carla is so dehydrated that she has lost a lot of weight because that fluid that should be in her body is gone. So she is not doing well. A couple of things that we're seeing that lead us to this conclusion that Carla is dehydrated. And again, remember, you do not need to list all of these, just list some examples and I'll be happy. We're seeing that her heart rate is extremely high. Her blood pressure is extremely low. This tells us that the blood volume is very decreased. So she's very dehydrated. She has very little blood to go around in the body. That's why her heart is working so hard and the blood pressure is so low. We're also seeing that her urine is very, very concentrated. This is because at the level of the kidney, at the level of the nephron, we're trying to retain any water that's left in her body and not make urine. Well, if we're not making enough urine, whatever we're going to be peeing is going to be very, very concentrated, very, very dark. So we're seeing that as a change with the urine osmolarity. We're also seeing that the renal retention of Na and volume retention, they're maximally activated because the blood pressure is so low. So we're really trying to hold everything, every bit of fluids that we have in Carla's body. Some of the signs and symptoms that we saw with Carla at the end of the hike, she was dizzy, tired, weak, nauseated. These all tell us because her blood pressure is so low, it's not enough to supply brain. So her brain is negatively affected by this low blood pressure. And we're seeing all these signs: dizziness, tiredness, weakness, nausea. We're also seeing that there's going to be loss of water from the cells, so the cells are physically starting to shrink. You remember when we talked about those skinny cells, hypertonic cells. So we're seeing that as well happening here. So remember, hypertonic cells, cells that were losing water, they were becoming skinny cells. So really what I'm looking for in this answer is, first of all, that you tell me that she has lost weight because she is so dehydrated. She's lost that water. It's water that she's lost. It's not that she became very fit or she became very skinny. She is just dehydrated. That's why she's not got the weight that she should have. And we're providing some of the examples that led us to this conclusion. And like I said, you don't need to provide all of them. You don't need to provide all of them in this detail. You just need to give me some examples. Why did you come to this conclusion? So that was Carla. And the final question, pair of questions that we should look at is what's happening with Maria. So let's have a look at what's happening with Maria. We see that Maria actually gained weight during her 8-hour hike. No, she did not build new muscle. She simply was drinking so much that now she's holding a lot of fluids inside her body. So it's all fluid weight that she gained. It's nothing, not a muscle mass or anything like that. So she is over watered, if you wish to say that. So we could use a clinical description of saying that Maria is now suffering from water intoxication. So because of water intoxication, we're seeing all these signs and symptoms: headache, vomiting, lethargy, confusion. They tell us that she is intoxicated. Anything can be a toxin if you consume it in high enough amounts. This is true also for water. If you consume too much water, it will become a toxic for your body. So let's have a look at some of the explanations why we came up with this conclusion. Her heart rate is low, even though we would expect it to be higher because she's exercising. It's just too low to make sense. So that tells us that there's too much fluids going on. Her blood pressure is elevated more than we would expect it to be. So that tells us that even though she's been sweating and she's been losing some volume, the blood pressure should not be that high. So it tells us that there's excess fluid in her body. And this excess fluid is being seen as excess blood plasma. So that's why the blood pressure is so high, and we would not expect it to be that high for someone who's doing this heavy physical exercise. We're also seeing that her urine osmolarity is low, so she has a lot of free water that she's peeing. Her urine is very diluted. She just has way too much water. She's trying to get rid of it. Her body is trying to get rid of it by urinating it out. And so we're seeing a lot of urine production. So all of these are reasons why we can say that, okay, what's happening with Maria is that she has just way too much water in her body, and that's it. So if you're able to give me that conclusion and back it up with 1 or 2 reasons, you're doing great. Please don't make this into a bigger of a deal than it is. This is simple lab. Even though it's a critical thinking assignment, that's more of a homework for me as your instructor than it is for you to get those points that I want you to get for this assignment. So that really completes everything that I had planned for explaining the homework, everything that I had planned for reviewing the chapter content, and everything that I had planned for reviewing the lab material. I hope you found that useful, and if there are any questions, I'm happy to answer now. I'm happy to answer later on. All you have to do is let me know. But if you feel that you got everything that you needed out of this, I'm very, very happy, and I hope you have a very good rest of the night. Like I said, I will upload these recordings to Canvas. It just takes me a little bit of time that it goes through the YouTube. I upload them there and YouTube processes them, but these recordings will be there, I hope, very, very soon, depending on the speed of the internet and what YouTube is doing. So this really concludes everything that I had planned. I'm so glad that it helped you. I hope you have a good night. Thank you again for joining me. I really, really do appreciate you being part of this course. And I know that you're going to get that good grade that you so deserve. So have a good night and take care. I'll see you next week. Thank you. Bye. And on that note, I'm simply going to finish off our recording for today. Like I said, I always want to make this worth your time. I don't want to keep you any longer than you need to be. I hope you found this useful. I'm here to help you every step of the way on your course. And I'm very, very excited to see the good work, how it's yielding so good grades. And I'm pretty certain that you're all going to be doing really, really, really well on this course once we get to the final grades. So please don't give up. Keep doing what you're doing, and let's finish strong this course. And have a good weekend and have a good night. Until we see next week, thank you and bye.